Yours?
Mine?
Okay. Should I use this one to talk? Okay. All good, or? You can hear me? Okay. Okay, let's get started. Today we have a lecture that continues my lecture. Geraldo, who is a PhD student who recently graduated. He's not a PhD student anymore. He's a postdoctoral researcher, but he worked with me. How many years?
Almost 8.
Almost 8 years, apparently.
1 month, 8 years.
Okay, that's right. Yes, he was an intern before he became a PhD student at Safari, but he did a wonderful thesis on the topic he's going to talk about, memory-centric computing. His thesis was on both hardware support as well as software support, like programming and compilation mechanisms for processing in memory techniques, both for processing using memory that you had seen last time, as well as processing near memory that you had also seen last time. So his thesis really covers a broad span, which is very difficult to find in general in PhD theses, hardware and software. It's difficult to write these in just one area. Geraldo wrote it in a cross-layered fashion. So he's going to talk about both some of the work he has done, but also some of the work that he has known. And he has given a lot of tutorials in top conferences on memory-centric computing. How many have you given? 7 or so. Okay, you're going to be part of one more. So, okay, at least one more. Okay, Geraldo, go ahead.
An honor. Okay, let's get started because I have a lot to cover, as you can imagine. We are going to dig a little bit deeper on what Onur discussed last time. So I'm not going to introduce myself. I'm going to give a very fast review of what was the previous lecture, just in case you forgot what is processing memory and memory-centric computing. But overall, the main problem that we're trying to solve over here is that today's systems are bottlenecked by data. And data is key in many applications. One key example is, as you can imagine, generative AI, where the demand for memory has been grown since the first instance of transformers in 2017. And the trend is not going to stop anytime soon. Actually, things are getting worse and worse, not for the domains of machine learning, but also other domains like bioinformatics, for example, what is over here. So the main problem that this amount of data, that huge amount of data generates in today's computing systems is that it wastes energy and wastes performance as well. Because of the way that we've been designing systems so far, which does not take data as a key instance of the system design itself. So you might remember this overall abstraction from Onur's lecture, where today we design, if you take a digital design class, you're going to see that you're going to learn how to design a system by separating computation, communication, and memory and storage. And we optimize, and we are very good at optimizing each one of those components individually. We have very high-speed computing, phone servers, very fast memory devices, very fast interconnects. But the problem is that individualizing those components is not enough anymore. And this problem is becoming a cross-layer problem across all of those three aspects themselves. So we need to now think about designing a system in a more holistic way, where we can co-design both computation, communication, and memory in a single system. My pointer just works from here. So just to highlight some numbers to see how much of this data movement is a problem, we did some studies together with Google back then on consumer workload for Chromebooks at the time. And then we saw that even in a small scale, like your Chromebook, Chromebook is a very simple laptop even in those systems, data movement was dominating for some key workloads. And if you look at specialized accelerators that are designed to be very efficient when accelerating one single application, in this case was the Google Edge CPU, as well for the edge devices, so they are supposed to be very high efficient in terms of energy. Those, for depending on the model that you run there, you also end up suffering from data movement related problems. So one way of mitigating this data movement bottleneck issue is what we call processing in memory. So this term is quite overused in the literature. You might see computing memory, processing memory, memory-centric computing, all of those referring to the same thing. But the main idea here is to move some portions of the computation to inside the memory arrays themselves. And by doing so, we generate a lot of different questions, which we are going to address over here in this talk. But this idea is not particularly new. It's not something that is being designed by my PhD thesis. Actually, it has been proposed since the 70s in those seminal papers over here. And there was some instance of this type of architectures coming back and forth in the computer architecture literature. So in the 70s, it was initially proposed. And then in the 1990s, there was a huge push from so some universities in the Bay Area with the IRAM and the DIVA processors. Then it died a little bit, and then it came back on the 2015s with the, or 2012 with the realization of 3D stack memory. And now we are starting to see product lines that are developed using these ideas in the 2020. So it's a great time to do research on processing memory. So this was, again, a very fast overview of processing memory architectures. And just to give a little bit more background on the literature, now we divide those processing memory architectures into two different types, depending on how the computation is performed, processing near memory or processing using memory. So processing near memory architectures is designed by adding computation nearby the logic itself. So here is quite similar to how we would design a processor with memory as is today. The main difference is the integration of that compute with the memory. So you design your logic and you design your memory, and you integrate that logic closer and closer to the memory arrays themselves. But still there is some separation, what is logic and what is compute. This is much easier to integrate in current systems, and is this type of systems that we are seeing reaching the market right now from main memory manufacturers. The other way of doing processing memory is what we call processing using memory. And here we forget the separation between logic and memory. So here we use the operating principles of the memory cells themselves to perform computation. And we are going to compose complex operations using those simple analog operations. So here there's no separation of what is memory and what is compute. The memory is the compute. So this enables a lot of parallelism to the system, and also at low cost, because you don't need to add extra logic for compute itself. You might add some modifications to the circuitry to do the computation more efficient, but the computation itself is just the memory cells that you have available. So in this way is very cheap to do computing like this, but it incurs other reliability issues and also some difficulty in performance in integration to current systems. So the landscape of both processing memory and processing near memory and processing using memory is quite vast today. I'm going to highlight some systems that we have available right now. For example, we have a system that uses memory extenders to implement processing near memory solutions. We have solutions from Samsung. There are actually an entire product line from Samsung that goes from the edge devices, so your phone, until regular laptops, until cloud servers. And each one of those devices have different properties to accelerate target workloads. In that case here is transformer. So either running generative AI on the edge, on your phone, or in the servers, for example. Another big push is via what is called 3D stack memory. So here is some package technology that allow you to design logic die and using what's called true silicon vias, merge this logic die with memory dies on top of themselves. So this type of, what is highlighted here is an old design called HMC, but you might have heard about HBM in your NVIDIA GPU architecture. So it's the same type of memory that is over there. And moving to processing using memory, which Onur presented as well last week. Here again, we are going to use the analog operating principle of the memory for computation. And we start with very simple primitives. First, we saw that we can do in-DRAM row copy operations by submitting consecutive activations to the DRAM chip itself. So the first activation copies the source row to what is called a row buffer inside the DRAM array. This is just how your DRAM operates. There is nothing new. What is new is that instead of just accessing columns of this DRAM and bringing those columns to the CPU to do a copy, we simply activate another DRAM row that you want to copy the source row to. This allows a connection between the row buffer to this newly activated DRAM row. And because of some circuit properties, the data that was latched in this row buffer from the source row is copied to the destination row. So here we can do this in DRAM row copy without involving the CPU in the process. So you don't need to move the cache lines to the processor. Which, as you can see, has we didn't add any logic to do such computation. And this is the row clone work, and then we can do more complex operations. For example, we can do in-DRAM and or operations by issuing triple row activations. So when you activate 3 DRAM rows at the same time in a DRAM array, those 3 DRAM cells are going to simultaneously perturbate the voltage level in a bit line or in a column of your DRAM array. And what we have in that row buffer that I mentioned is basically a differential sense amplifier. So these 2 back-to-back inverters here that operates kind of as a majority circuitry. So this sense amplifier is going to pull that voltage level to the majority of the voltage stored in the DRAM cell. So in the example here, you can abstract this to, we have stored 1, 1, and 0. We activate those 3 cells at the same time. They are going to perturbate the DRAM color or the bit line. This perturbation is going to be sensed and amplified to the majority of 1, 1, and 0, which is going to be 1 in this case, or VDD. So by controlling one of those rows, we can either perform a OR operation or a AND operation. And this is the ambit work. And we can use these operations to do more complex things. So if you have copy, we have in-DRAM and or. I didn't mention here, but ambit also show how you can do NOT operations. So if you have if you have NOT and or, we have an AND, which is in theory functional complete. So you can theory implement any complex operations as you want by composing sequences of AND, OR, and NOT operations using those primitives that I just mentioned. And this is exactly what we do in this work called SIM-DRAM. So let's say that you want to implement an in-DRAM addition operation that is going to add 2 vectors, vector A and vector B. Each one of those vectors have many elements. Each element is stored in one of the many DRAM columns in the DRAM subarray, but all of the elements only have 1 bit. So we're going to do just 1 bit operation. So what we propose in SIM-DRAM is to first, you get the Boolean circuit that can implement that operation that you want to do. So in this case, a RIP carry adder here, and then using some equivalence, you convert this circuitry into the same circuit, but that only contains a majority NOT primitives. Why only majority NOT? Because as I mentioned earlier, the operation that you are doing when you are doing triple row activation in the DRAM array is basically a majority of 3 operations. So this is going to allow you to do a more efficient computation because we don't need to control one of those rows to do AND and OR. So this reduces the latency of the operation. So after you have this RIP carry adder here that only have majority NOT circuitry, what is left for you to do is go through this graph and issue triple row activations to the DRAM array according to the input of the circuitry. So here, for example, the first majority gate have as input A, B, a carry in. So A and B has 1 and carry in has 0. The majority of 1, 1 and 0 is going to be 1. And we are going to store this in this carry out row. Then we move to the next and the next case, in this case 3, I'm skipping to the result. So in the end, we are going to have 1 row with carry out of 1 and 1 row with the sum of the operation as 0. And the way that you read this is in a vertical way. There is some issues related to bit shifting operation. So we are storing the data vertically inside the DRAM columns. And if you read that data in a vertical way, so here we have 1 and 0, which is 2, which is the result of the addition operation of 1 and 1. 1, 1 is 2 in Boolean logic. Okay, if you want to do a n bit operation, so I showed how to do with 1 bit, we can just repeat this procedure n times. So if you want to do a 32-bit addition, you just keep repeating these triple activations of this circuitry 32 times. And if you want to do a multiplication, you do it n squared, so 32 times 32 times. So basically, by operating the DRAM chip as we are proposing over here, we can see the DRAM array now not only as a way of storing data, but we can see the DRAM chip as a very wide bit serial engine. So the engine is as wide as DRAM columns that you have in a DRAM subarray, which is around 65,000, where each one of those columns in the DRAM subarray is going to be a SIMD engine itself. And note that here we are not including any hardware to do this majority of 3D. We are just using what's already there in the sense amplifiers of the DRAM subarray itself. And this is the SIMDRAM work. So we have further improved on top of these substrates to be more efficient and allow us to implement multiple structure, multiple data computation in the substrate by segmenting what's called a DRAM mat, or the many DRAM mats in the DRAM subarray, and allowing them to operate individually. So think about taking those 65,000 columns that I just mentioned and creating blocks of smaller granularities of 512 columns at once. This allows you to better map applications to the substrate and improving SIMD utilization for a single application. And if you have two operations that are data independent from each other, you can execute those 2 operations at the same time in different groups of those 512 columns inside a single DRAM subarray in what we call a multiple instruction, multiple data execution model. This also allows us to do reduction operations inside the DRAM subarray. I'm not going to get into details on how this goes about because I didn't give the proper DRAM background. So just hopefully believe in me. And also allows us to ease programmability for this type of substrate. I don't know if you are familiar with vector programming in Intel or ARM processors, but over there we have SIMD engines themselves that operate around 512 SIMD lanes. So Intel have, for example, AVX 512 instructions. So we can take those instructions, not necessarily exactly the instruction, but the infrastructure that is built around to generate those instructions to also generate code for this DRAM substrate as well, using compilation transformations that we implement in this work. So all of this is just to highlight that our DRAM chips are already capable of performance computation as they are today. We have been conducting experiments with real commodity off-the-shelf DRAM chips in FPGA-based platforms, and we see that they can implement, for example, in DRAM row copy, perform NOT operations, and also multiple input and NAND or NOR operations by violating DRAM time parameters. So as they are, so the DRAM not necessarily of your laptop, but of some initialization of some instance of a particular DRAM chip can already perform this as we are proposing over here. Not exactly, but operating in a similar way. So this is brings me to the adoption issues. Is there any question related to the background that I just mentioned?
So for 32-bit multiplication, you mentioned that you require 32 square.
32 square, yes.
So for 64-bit, you will require
64 square, yeah.
So then, is there any explores the interaction between processing and using memory and RowHammer approaches because they require a lot of row activation.
Yes, there is. It's not here in this work. We had a work called RowHammer that shows that multiple row activation can unfortunately generate bit flips. But yeah, so I think, I don't know, maybe it's going to be one of the required readings during the semester. So I'm not going to spoil that over here. But yeah, it can create this problem. Yeah. Yeah. Question over there?
How do you know when the operation is finished, especially if it's not like a bit plus operation, but like a repeat period, where you have to wait n or n squared time?
So I went quite fast over here, but on the background. But what we do is that we compose what is called a micro program, which is a recipe that tells the memory controller which sequence of activations needs to be issued to the DRAM chips to do a particular n-bit operation, and over there that n is specified. So the memory controller knows because of that recipe when to stop. There's actually a flag there called done, and then you're done. But that is on the details of the design itself. The good thing about this is that the latency is quite predictable because we always know the latency of activation, and we always know how many of those triple activations we need to do based on the inputs that you have and on that graph that I showed with the circuitry. So we can always predict when it's should finish. Any other question? Okay, this was hopefully an overview of what was presented last week. But now I'm going to start with this talk itself, is how actually we enable those systems. Okay, I'm showing you here that there is this great new architecture that can do wonders with very low costs. But why they are not yet on your phone, right? So what is the deal? So the problem is that we need to solve several adoption barriers before adopting those systems. This is already a spoiler of what I'm going to ask next. But the first question of adoption is this application good for everything? Or is any application that you want to run, I don't know, PowerPoint? Is PowerPoint good for running on this type of processing memory system? Or is, I don't know, Chrome good enough to run? So where is how is there any thoughts on how should I know if the application would benefit for this type of architecture or not? Or do you believe that this is good for everything and I can just ditch my Intel processor or my MX processor and just move there? Any thought?
One end would be if the computation is data movement bound.
Yes, that's definitely the key, right? If the application needs to be data intensive. But then the question is, what does it mean to be data intensive? How I quantify data intensiveness?
You can check the peak hardware utilization. If the peak hardware utilization is nowhere near maximum, let's say below 5%.
I can do top and look at the CPU utilization, for example. But what exactly this is telling me, right? So so the processor is not only memory or CPU, right? So there are other components that tells me that my utilization might be low. For example, there are applications that are very high on speculation. So your processor is trying to figure out which path should it take to go, because there are branches in your code, there are if statements, and there is a logic over there to figure out if I go to one path and to another. And this also can create a bottleneck. And even if you do top and look at the utilization, is going to be low because I'm not doing computation, just trying to figure out where to go. So that is one good indication, but it might be something else as well. It does not necessarily tell you that you might be memory bound, but you are in a good direction. The thing here that I want to highlight is that we need to figure out applications that are data intensive, they are data intensive, but how do I quantify that? How I can tell, and how do I put a threshold? Or this is data intensive, this is compute intensive, and that's very tricky to do in a quantitative way. for a given application. And this is what we are first trying to answer in this work called DAMove, where we show that current tools are not very good at telling you if application is data intensive or not, and can benefit from these process memory architectures or not. So one example, if you are into GPU programming for neural networks, you might have heard about this roofline model that I'm showing over here. This model is quite a simple model. It's just telling you here in the x-axis the arithmetic intensity of our application. So how many operations, arithmetic operations are you doing per bytes that you load for your RAM? So if you do a lot of operations per bytes that you load from your RAM, you're good, right? You're not having underutilization. This is one metric for that can tell you how much you're utilizing of your resources. And then in the y-axis here, we have the performance of your application in gig operations per second. And then there are two roofs in this model. This first roof here is called a compute roof, and this is equal to the peak system throughput of your application. So if your application lies below this compute roof here, it means that your application is compute bound. So I'm loading a lot of data. I'm loading some data, and I'm doing a lot of computation on this amount of data that I'm loading. And this is giving me to some X performance here. If there is another roof, which is equal to the bandwidth of your RAM times the arithmetic intensity of your application. If you are below this roof here, you're loading some data. We are using that data, and then you trash it. Then you load another data, you compute, and then you trash. And then you load, you compute, and then you trash. So if this is happening to your system, you're likely memory bound. So RAM might be one particular issue from your application. So we took this model. This is not what we are proposing. We took this model. This is a quite well-known model to identify if your application is memory intensive or compute intensive. And we profile a bunch of applications. And we see if those applications would benefit from process memory or not. So applications in blue here are those that are faster to run on the regular CPU, and the ones in orange here are the ones that are faster running on the pin system. And there are some corner cases here that depends on the configuration. So what we see here is that there are a couple of applications that if you take this model as it is, there are some couple applications that, yes, they are below this memory roof here, and they run faster on the process memory system. So that's what we're expecting, right? There are some other applications here that are compute bound, so they are bottlenecked by the compute of the CPU. So they don't necessarily benefit from the pin system, which is also what we were expecting. But there are a lot of applications that are kind of like noise here. So applications that are memory intensive according to this model, but sometimes the performance of the pin system is better. Sometimes the performance of the CPU is better depending on the configuration or the input size or the number of cores that you have available in your system. And the opposite is also true. Sometimes the whole system is better than the whole system for those compute-bound applications, but depending on the number of cores as well, or the configuration of the application, this might flip. So this model here is not comprehensive enough to tell you if a memory-bound application, to whatever definition of memory-bound or memory-intensive this model is giving to you, this is not good enough to indicate if application is performant in a processing memory system. So this is one way of doing it. Another way is looking at a given metric. So there is a metric that it's called last level misses per kilo instruction. So that's very mouthful, but basically I'm going to give an intuition. So you are looking at the memory bus and you're trying to see at every 1,000 instructions, how many of those instructions are memory instructions and they are showing up on my memory bus. So if, I don't know, this metric is very high, you can mean you're going to intuitively believe that there is a lot of communication between your host, your RAM, because there's a lot of data being fetched to the CPU, to the RAM. So your application then is memory intensive, right? So you're using the bus. So this is one metric that gives some insight about that bus utilization in a very simplistic way. So if you look at the definition of memory intensive based on this metric here, and we look at those applications with high less level misses per kilo instruction, so the utilization of the bus is high, those applications benefit from process memory, which is expected. And applications that this metric is low, but whatever threshold that we are using here, in this case 10, they are mostly benefiting from the CPU system. So they are not, those applications are not generating very high memory traffic. But there are applications in using this model here that the less level misses per kilo instructions is low, to whatever definition of low that we're using, but benefit from process memory, or might benefit depending on the configuration. So again, if you look at a single metric, that's the key here. You look at the single metric, it's not enough as well to give you the big picture of what actually is the memory intensiveness definition that you are looking for when you're trying to understand if application benefits from process memory or not. So this leads us to the problem statement of this work, is that there are actually no single methodology that can tells you with some high guarantees that it can give you a good definition of memory intensiveness that translates to process memory suitability. And this is what we're trying to come up with over here. What are the metrics that we actually need to look to create this definition, and also to allow us to compare data-centric and memory-centric systems. So to this end, we propose the move methodology, which is composed of 3 main steps. So we have your application, and then in the first step, this is completely optional. You just profile your application, and there are some functions in your application that's taking the most amount of time. So we identify this function first, so just to reduce the search space. Then we have a simulator called the move sim that generates first memory traces of the memory access of your application, and then performs 2 types of analysis. The first one is a locality-based analysis, which you are going to look at the properties of the memory trace itself, so the properties of the application, and we are going to try to quantify if the application has good enough locality to benefit from whatever is there on the CPU system. Then we are going to perform some microarchitecture analysis, and we are going to look at system level metrics, like exactly the metric that I just mentioned before, the less level misses per kilo instructions, but also other metrics to try to give us an indication on how that system behaving when you're running that particular application. And by combining the data that we collected from those 2 steps, we classify the application in 6 different classes of data movement bottlenecks, and each class of data movement bottleneck may or may not benefit from process memory, depending on the system configuration. So I am going extremely slow, and I have a lot of slides to cover, so I'm going to go very briefly over here. So in the first step, we use some profiling tool to allow us to figure out which functions of the applications are actually interesting for us to look at, because we did this study over 300 plus applications. So if you look at every single function in those 300 applications, we had 77,000 functions. It's too much for the design space. So this is mostly a filtering step. Then we generate that memory trace of the application, and we compute 2 metrics, spatial locality and temporal locality. I'm not going to give the definition of what this metric actually is, but I want to give the intuition why spatial and temporal locality is important. Does anyone know why it is important before I give the intuition? Have anyone, did you guys took the computer digital design class? So
spatial locality is more related to how the data is placed. So if you have good spatial locality, you will load less into the cache from the main memory. So that way you have more reuse, and you can basically run faster if your data. Exactly.
So we design everything, hopefully, we design cache systems, right? And we hope that the data is going to be in the cache, which is fast. And the entire intuition behind the cache is that it captures this particular reuse in terms of distance of access, and also how many times you access the data. So if you don't have spatial and temporal locality, your caches are useless. If your caches are useless, you're going to the DRAM most of the time. So this is why you need to quantify this spatial and temporal locality. And note that this is a property of the application, not necessarily of the system. Your application, depending on if you are writing the code that traverses a graph that is quite random, or if your code is traversing array that is quite sequential, that's going to impact your temporal and spatial locality. So this is why you are trying to capture properties of the application itself over here, independent of the system. So the first step uses some histogram of reuse and stride profile distribution to generate a value between 0 and 1 and tells you if this application has high or low spatial and temporal locality. Then we do some simulations. And then we profile this application running on the system, so system-related metrics. So one metric that we already looked at before was less level cache misses per kilo instructions, MPKI, which shows how many instructions are memory instructions in the memory stream. But there are also other instructions, other metrics that we look at. For example, arithmetic intensity. This metric here is the x-axis of that roof line that I just mentioned some slides ago, right? And there is a new metric called last to first miss ratio, which is the ratio between last level cache misses by L1 misses, that tells you how many of those misses are being captured. Misses generated by L1 is being captured throughout the cache hierarchy. Which also is a good indication if your caches are being effective or not for that given application. And by combining those metrics in a single model, we can classify in a more holistic way different sources of data movement in your application, ranging from something simple like DRAM bandwidth for latency bounds, or something more complex, like, for example, cache contention. So if you have a multi-threaded application with many threads and they start contending for a shared resource, that itself might generate memory bottleneck for your application. So this is one thing this model captures and prior models would not capture with a single or two metrics. Question?
What is why would a low temporal locality like correlate with memory bounds application?
So if you have low temporal locality, it means that you are not going to that, you are going to that cache, but you're not finding the data there. So you use the data only once or twice. So remember that x-axis with the reuse. So you are loading the data once, doing a computation, trashing, load the data again, or another piece of data doing computation, and so on and so forth. Other question? Okay. So we open source this methodology or simulator, and also we did this analysis. We use this methodology to do the analysis of the suitability of process memory for more than 300 applications, and we collect those applications into a benchmark suite called the Move benchmark, and everything's available on our GitHub repository. And if you want to learn more, there is a very long COVID lecture that I gave about this when I was blonde for some time. So another way of trying to figure out if application benefit from process memory or not is just to run the application, right? So you just take X amount of applications, take the system run, and compare the performance of that particular system with the regular CPU system, right? So this is what we did initially when the MEMP system was released. So this is some processing near memory architecture that adds some general purpose core near the DRAM bank to the DRAM chips. So we had access to these systems, and we did some extensive analysis. So this is how the system looks like. We did some extensive analysis and benchmarking where we port 16 different applications over here that we thought that might benefit from this type of system to that system, and then we compare these applications to the regular processor-centric architecture, like CPU and GPUs, and this allows us to review some limitations of that architecture itself in this benchmark suite called Prim. So this is a more almost ad hoc approach of the same problem that I mentioned in the Move here. Here we're just testing and seeing what happens if you run that application over there. So it does not necessarily give you much intuition on what might be a general approach for understanding processing memory suitability, but it's still one way of conducting research. So those are the 16 applications that we implemented. And since then, we have been studying the system and porting more different applications over there. So we start very simple with very simple kernels. And then as we understood the system, we progressively make those applications more complex. So including some machine learning applications, some sparse matrix vector multiplications. There are some bioinformatic workloads, translation logic. So this is just a list of the applications that we ported over there. Okay. So this solves, that not necessarily solves, there is still a bunch of questions related to applicability, but it gives you some hints on how we solve the first, how we can solve the first adoption barrier for processing memory. So now we have a framework that at least can tell you if this application, if a given application might benefit from this new architecture or not, right? Okay, now I know if this application would benefit or not. Now is the time to port this application to the hardware itself. So how you do it? How you program this type of system? Questions?
So in the previous section, we saw on the basis of arithmetic intensity whether it is beneficial to go PI or not. But then there are other techniques like fusion, which can actually increase arithmetic intensity, and then that can make things faster. So do we have something to compare with those things which can artificially increase artificially increase arithmetic intensity against the usual PI method without doing fusion or any other?
Yeah, but you can when you usually do fusion, for example, you do like as a either you do manually or you have a compiler pass that does it for you, right? So when you're looking at the applications here, is like the compiled version. So that is, if you have fusion mixed there, it's just going to be captured in the profiling of the application itself. So usually we don't try to individualize the optimizations that one might apply to the code itself or the compiler might apply, because there are so many of them. I don't know, loop unrolling or loop, there is something called fission as well. So that would be very hard to distinguish each one of them. So you always look at the final binary that's produced, and that does not make any difference what was being applied, because we're just looking at the sequence of instructions. But yeah, great question. Any other question related to methodology? Okay, so now let's see how we can port the application to this system. So let's start very simple. Let's do minimum modification to the hardware device and allows that modification to be visible to the software itself. So there's this, for example, let's say that we have a page rank code. So this is the code of page rank that goes to a node in a graph and updates a particular value in each one of the vertices in that graph. So the operation that is being performed here is quite simple. It's just a simple add operation to a scalar value. So we can replace this operation by a simple spin add operation that does that update for us itself. But this is just one instruction. And by doing this, we can simplify a lot of system design constraints. Since we are only update a single scalar value, we don't have to bookkeeping a lot of data, and we don't need to worry about coherence for big regions of data or virtually generating code for generate virtual address or mapping virtual to physical address to that particular range, because again, it's just one simple instruction that does a scalar update. So this is also atomic operation, meaning that this guarantees consistency when you are distributing this computation across many different computing elements in the system itself. So this is all of this is just to say that if you do a minimum, if you allow the memory to do a minimal thing, which is a scalar update in a single value that's storing a given memory bank, this is very easy to program because it's just one update in the code, and it's also very easy to support system-wise because it's not touching a lot of data. It's just going to touch 8 bytes of data in one particular memory bank. And then over here. Yeah, so this is what I just mentioned over here. And this is the design of the system. So you have a 3D stack memory device, and then nearby the memory controller, you have some of those, it's very simple logic to do this atomic updates. And you have that same unit nearby the processor. So we can decide based on the locality of the application, where the application should be executed. And by doing this, we can have very good performance improvement. But there is an issue with this type of system in terms of, maybe I ask for, what do you think might be the issue of doing something that simple? If I'm just updating 8 bytes of data at a time? So if you read a cache line, maybe you don't know, I don't know how much you know about the DRAM organization, but usually the bus is wider. So if you open a row, you open 8 kilobytes of data, and when you read the cache line, usually you read 64 bytes of data. So if you only operate over 8 bytes, for example, you're basically having underutilization of your internal bandwidth of your DRAM chip. So it goes against the purpose of maximally utilize the internal bandwidth of DRAM to accelerate the memory intensive application. So this is good, but it caps the performance that you can get from your pin system. So after the break, we are going to look at more complex way of programming this type of architectures. So let's come back at 5:15, and I'm going to try to be faster next time. Okay. Welcome back. I'm going to speed up a little bit. I'm very sorry. But the question that you are trying to solve now is of adoption is how to program those systems, right? How to the programmability. So let's look at the mapping system as an example. This is true also for other process memory architectures. So we have this new system, right? How you program those systems. So the system has its own complexity itself, but the way that you program them are as if they are side accelerators, meaning that they have their own memory address space, they have their own programming model, and usually there is a separation. Can be very coarse or very fine between the memory address space of the processor and the memory address space of the pin system itself from some other system integration challenge related, for example, to consistency and coherence. But basically what that all means is that if you have one of those systems, you need to, as a programmer, figure out which portion of the data is going to be offloaded to the particular pin hardware itself. Then you need to transfer that data to whatever it might be initially to the where it needs to be. So in the pin system, this is more coarse-grained because there is a physical separation between DRAM memory and pin memory. But it does not need to be. Even if you have a single DRAM chip, you might need to move the data from one particular DRAM bank to another where the computation is. Then your pin system might have some sort of memory hierarchy inside itself, and you might need to handle that memory hierarchy as well. In the pin system, there is some SRAM that operates similar to a scratchpad memory that you need to manually put data over there. And then once the computation is done in a particular pin unit, you might need to copy this computation back either to the destination or to another pin unit, or basically handle the outputs that is generated. So let's see how this translates to coding itself for particularly the mapping system. I'm going to show you a bunch of snippets of code, and I don't expect you to understand a single bit of that other than the fact that it's a lot. So let's say that you want to write a vector addition code for the mapping system. This is already a simplified version of the code that you need to write. But basically what you need to do is that you have your input arrays. You need to align them to the boundaries of the DRAM bank. You need to collect input parameters from the pin units, distribute those parameters, launch the computation, collect back the results, manage the scatterpad memory in the mapping system, orchestrates the internal computations across the process memory cores, and you, as a coder, just wanted to do this vector addition. So you just wanted to write at most, I don't know, 4 lines. If you remove, you can even remove this. It was like, I don't know, 2 lines of code, but you have to be keeping all of those other lines of code just to manage the device itself. And this is not static. This is going to, of course, going to depend on the computation that you need to do and how data might be organized. So basically what I'm trying to convey here is that programming those systems, even though might be intuitive to some, is not trivial and requires a learning curve to learn that programming model and understand not only that, also you need to understand the underlying hardware that you have to manually orchestrate internal data movements and also computation. So the goal of these works that I'm going to show here is to ease the programmability of those process memory code or process memory architectures by abstracting that computing paradigm a little bit more, because right now it's too low level. So how you do that? So the first way that you do that is this work called Simple PIM, which basically provides some APIs to the user to program the mapping system. So Simple PIM implements 3 main APIs. The first one is a management interface API that just allows the user to register which arrays are going to be used for process memory computation in the application. Then there is some communication interfaces API that gives user the ability to communicate or to share data across pin cores or across the whole system and the pin cores itself. And there are some processing interface that allows the user to do simple computations, simple parallel operations like map, reduce, or zip. There are a lot of other code optimization that this allows us to implement, but I'm not going to get into details over here. What I want to show is that if you use this application, so this is another code example, simplified, because there's some dot here, for histogram code that executes on the mapping system. So if you use that same, this set of APIs that I just mentioned here to write the same code, we can simplify that code to basically some function calls to do that same type of computation. So this is very good. This reduces lines of code to write some simple kernels compared to hand optimize significantly, and also allow us to have on performance comparable to the hand optimized code because we apply some optimizations in the back end that I didn't mention over here. So this is good that this is open source, but this is still this is quite limited because, as I mentioned in the one of the APIs, the user still needs to identify how data is communicated across the different pins, pin cores, and use. You don't have to write the code, but now you still need to identify those communication patterns and use those communication interfaces, and also needs to manually manage computation or arrays that are going to be resident on the pin core itself. So there is still some degree of knowledge that the user needs to have in order of the underlying architecture to write codes to the system. So let's see how we can abstract that even more. So we move to Dapper, which is going to take this idea of skeleton. This is something quite common on the parallel programming, not only for PIM, but for GPUs, for example, called skeleton-based programming. So you take some parallel primitives, and then you provide some skeleton of the code that needs to be generated, and based on those primitives, you generate the code for the architecture automatically. So this is exactly what we're going to do over here. So basically, we provide the user 5 main data parallel primitives on how computation is to be orchestrated. So those, for example, being a map. So you take 2 arrays and you generate another array. Reduce, you reduce array into scalable variables. You filter some array values through a filtering function. You implement some type of slide window type of computation. Think about convolution, right? So you always sliding a convolution window to a matrix, or you group some computation. So those are quite common parallel patterns in parallel programming. So this is not related to PIM itself, but we are going to use these primitives. We're going to give the user these primitives and allow the user to describe which computation needs to be performed in the PIM system. And based on these primitives, the framework is going to automatically generate the code. And this code generation is generated based on this data flow parallel programming interface, where the user uses those primitives that I just mentioned, map, reduce, filter, group, window, to define stages of computation. And each stage operates as a pipeline. So data flows from one stage to another until the output is generated. And then, based on after the user writes down these stages, we can automatically generate that data management code that I mentioned earlier in the motivation to the up mapping system, while implementing some optimizations in the back end to further optimize the code. So this is, again, just an example on how that operates. So let's say that you want to, again, implement some dot product, simple array-based operation. So have that dot product operation that you want to implement in the PIM system. So the first step of you as a programmer is to identify, okay, this is what type of data parallel patterns I need to represent a dot product operation. So in this case here is a map and a reduce. So you pick the map and the reduce, and you implement the data flow programming interface. Note here that the code does not tell you anything related to the PIM hardware itself. It's just telling you, I have this array A, this array B. You do a multiplication between those 2 arrays, generate C, and then reduce array C into a scalar, which is called sum, and that's it. This is implemented the dot product operation. So and then this is what the user writes. So in the back end, we perform a bunch of code optimizations to figure out how the data needs to move inside this pipeline, and generate the appropriate up-mapping code via techniques like stringification, memory arrangement, and type removal. And then you generate and compile the codes to the up-mem pin system. Very important to notice here is, again, in what the programmer is writing, there is no intuition whatsoever of PIM here. It's just data parallel programming. If you have different PIN systems in your available to you, here I'm using the up-mem PIN system as an example. But if you have the Samsung, for example, you just replace this template generated here to the up-mem PIN system to a template for the Samsung architecture or to any other PIN architecture that you might need to do. So you might need to rewrite the back end, but the front end is the same. Which allows for generability to other, portability to other PIN architectures. So again, we evaluate this using some workload from the PRIM benchmark that I mentioned earlier, and we see that because of some optimization that I didn't mention here, that the backend can implement, because the code now is also standardized, we can improve performance while significantly reducing lines of code as well. So you write, like compared to what I mentioned earlier, you write what, 5 lines of code.
Are those primitives composable?
Yes, there are rules for the composing of them, but you can have like something like a window and a group, or a window a group and a filter. And in the paper we explain all of those mix and matches. Something that is very hard to do here is pointer chasing. That's very hard to do because you don't necessarily know. It's very hard to compute the boundaries of where the offset should be. So, but there are parallel primitives for that as well to handle this type of case. But it's not very efficient. But anyway, I digress. But yeah, they be composed. Any other question? Okay, so this, now we have a solution for, we know how to identify if application is memory bound. We also, if you identify that application, we have a way to easily program that memory bound application into our PIN system, right? The next question that you need to solve, which I'm going to not mention here because of time, is system and security support issues, which are very, very complex to solve. We have solutions for example, how to maintain data coherence. So if you have your CPU with its caches, right, and you have PIN in the system, and they are working together in the same task, and portions of the data is in the CPU caches and portions of the data is being updated by the PIN unit, how I guarantee that the data that the host sees is the most up-to-date one, or without incurring significantly performance degradation to the overall execution of the task. This is quite complicated to do because now we have a very distributed system. You have computation everywhere, and you don't have a single directory that you can keep track of where a particular piece of data is at a given moment in time. So it's a quite open topic on the subject still. Also, synchronization is very hard to do. This leads us to pointer chasing problems that also require virtual memory, and also code and data mapping. So all of those I'm going to skip because those problems are very complex to explain in a short amount of time. But probably some of them are going to be required readings during the seminar this semester. So you're going to have more chance to know about them. So now let's believe on me that we fixed the the coherence coordination virtual memory issue as well. The next question is runtime. So how do I maintain, how do I can optimize the execution of my application given data properties? How can I leverage components of the data itself to optimize the computation? So particularly those bit serial processing using memory architecture that I mentioned earlier, they have some limitations that some of you guys actually already mentioned, for example, related to the quadratic nature of multiplication. But not only that as well. So if I want to do a 32-bit integer operation, as I mentioned, the latency is going to grow linear with those 32 activations that you need to do for the computation itself. And usually you write in a code, right, int 32, or like, I don't know, when int 32 array A, B, C, and D, right? So you specify in the code itself what is the granularity of the computation, how many bits needs to be executed for that particular computation in a static manner. Even though in a lot of cases, I'm going to try to show you next, a lot of times you don't use those 32 bits to store the data, but that is defined statically prior to the computation. There is this throughput problem related to quadratic scaling computation and also scalability challenges. I'm going to motivate each one of them, those issues next. So there is this thing in computer architecture called narrow values, which is exactly this phenomenon that I just mentioned. So programmers tend to store narrow value, so small dynamic ranges inside large data values. So when you instantiate an integer, you're not necessarily thinking what are actually the boundaries that the integer might take during the execution of application, right? You're just using an integer because you believe that is what you're going to need. 32 bits should be enough, right? But you usually don't think about the lower end. So actually, how many bits do I need to store the integers that this code that I am writing is going to experience? So this generates what is called narrow value. So let's say that you have array A or a scalar value 8, with 8 bits. And this A value here only store the value 4. Over here. So you only need bits 0, 1, and 2 of that 8-bit scalar value. So all of the remaining bits of the scalar value is going to be all full of zeros. Still, you store the entire 8 bits in memory, right? And if you want to do addition operation doing processing memory over this computation, you're going to start performance a lot of activations over what we call inconsequential bits. So those most significant values here on the data does not necessarily contribute to the precision of the computation, but still you need to execute them because you don't know if this is going to be 8 or if it's going to be you're going to have a 1 here in the most significant bit, right, prior to the computation. So to guarantee correctness, you need to go through each one of those bits doing that bit serial activation mode that I mentioned earlier. But they generate latency and energy waste for your bit serial system. Note that in a regular scalar bit parallel way of doing computing, so in your scalar ALU in your processor, this is not much of a problem because you're performing those 32 operations at once, so you're not serializing them. Still, there are optimizations based on these narrow values for those bit parallel arithmetic units, but I'm just digressing again. So this is a problem that those bit serial processing memory architectures are going to face. And we do some analysis on real applications just to show how much of the problem exists for many applications. So we take many applications and we generate these plots here, which shows the bit precision distribution that arrays in that application might display over its execution. So as you can see here, several of those applications display a significant amount of narrow value. So in several of those applications, we can actually reduce the precision from 32 bits integer to, I don't know, in x64 to 8 bits. Or in this other application here to, I don't know, 22 bits at most. We don't always need those 32 bits doing the computation. What this allows you to do, it basically, if I can know prior to issuing those in-DRAM row activations, what is the precision of the operation, I can stop the the sequence of in-DRAM operations that I'm issuing before reaching those inconsequential bits here. So I can terminate the computation earlier, basically. And this allows me to save latency and save energy because I'm not issuing triple row activations or in-DRAM activations to rows that only contain zeros. So basically, I can. This is the entire idea over here. The question is how you can identify those values prior to the execution, and we're going to get to that later. So the second issue that we have is carry propagation. So since we are performing the operations here, there is bit by bit, and if you have our operation like addition being implemented using a RIP carry header, we are going to eventually need to propagate data generated from one bit, so the carry out from one bit to another bit. And this creates what we call here this inter-bit dependence, which serializes the latency of the entire operation. And this is problematic if you have a single DRAM subarray being used for the computation. So here, again, I'm just showing the example of addition. And in the other side of the slides, I have what the operations are being issued in each DRAM cycle. So as you note here, I issue 3 DRAM operations here until I can generate the carry, and then after that, I have my carry out bits being generated from bit 0 to the next bit, and then I can start doing operations for the follow-up bits in a serial manner. However, if you just look at the graph of the in-DRAM addition operation, if you disregard that inter-bits dependence operation between the carry out of one and bits to another, you have some majority gates here that they are quite bit independent. They don't once that carry bit has been propagated, those majority gates become independent from each other. So in theory, if I can distribute the computation, I can execute those majority gates in parallel once I fix the inter-bit dependency. So the main idea over here is to leverage what I just mentioned, and instead of using a single DRAM subarray, is to use multiple DRAM subarrays to do the computation, and where we are going to distribute the data from a single data word across the many DRAM subarrays. So here, bits 0 are stored in subarray 0. While bit 1s are stored in subarray 1, and bit 2 are stored in subarray 2, so on and so forth, in a round-robin fashion, depending on the number of bits and the number of subarrays that you have. And then we are going to also use some low-cost interconnects, which allow us to quickly move data from one DRAM subarray to a neighboring DRAM subarray. What this allows us to do is to actually break that dependency chain and parallelize the primitives across different DRAM subarrays. Because first I generate the carry bits in the first DRAM subarray here. Then I copy that carry bits to the other DRAM subarray that has data from the follow-up bits in the bit precision. And once this is copied, the carry out is propagated, the dependency chain is broken. And now I can concurrently execute those individual majority gates here across different DRAM bits at the same time in neighboring DRAM subarray, hence allowing me to save DRAM cycles for this bit 0 operation over here. And the third thing that's problematic is that, as I mentioned, the latency scales either linearly or quadratically with the bit precision. And even though we can reduce the latency using those two techniques that I just mentioned, use either early termination using error values, or using this parallelization method that I just mentioned here across different DRAM subarray, in the end, if I have operation that actually requires those 32 bits, I'm going to end up having this serialization and linear or quadratic scaling computation. So to solve this issue, we need to move from the standard two complements data representation format to other representation formats that does not carry this carry propagation across arithmetic operations. And that is a representation, a data representation format called redundant binary representation, which uses positioning of each bits to represent one bit represents one position represents 2 bits. So instead of using 0 and 1, it uses 0, 1, minus 1, and 0, 1, minus 1. It's only these 3. There is another one, it's 4. I forgot which one. Because 0 is represented twice. So 0, 1, 0, and minus 1 to represent a single digit. I'm not going to explain how this works. I just hope you believe on me. This comes from circuit design. But basically, since there is redundancy built on the data representation itself, this means that when you do arithmetic on top of this data representation, the carry change is limited to at most 2-bit positions. Independent on how much the precision grows, you only need to propagate carry for at most 2 bits. And this is, again, there is some mathematical formulation that explains why this happens, but it's just a property of this type of data representation formats. So all of this is to say that if I cannot reduce the latency of these bit serial operations because of the first 2 optimizations that I just mentioned, because I actually required higher bit precision for my computation, I can move from the regular data to complement data representation to this other data representation format over here that gives me constant latency for high precision computation. So based on all of these ideas, we designed this framework called Proteus, which is a runtime framework that dynamically and transparently adapts the implementation of the in-DRAM operation that you want to execute. They identifies the bit precision for the computation and also the data format either to complement or redundant binary representation based on the input data for the processing memory execution. So the framework is composed of 3 main components, which I'm going to illustrate over here. So first we have what's called parallelism-aware microprogram library. This is basically a collection of different implementations of arithmetic in-DRAM operations using different algorithms. So either use bit parallel algorithms like RIP carry adder, or bit serial or bit parallel algorithms like, I don't know, Cogar-Stone adder. And each one of those algorithms has different trade-offs depending on the target bit precision of the computation itself. And this is an offline step. So the important part here is this dynamic bit precision engine. So what is maybe is hidden in all of this talk that I gave so far is that there is a data layout transformation that happens that needs to happen for those processing memory operations to execute. So data needs to be placed inside a single DRAM bank, inside a single DRAM subarray in a vertical data layout prior to anything to happen. Otherwise, I cannot do the computation. So this means that there is some transformation that already happens to the data once before the processing memory instruction is executed by the memory chip. So what we are going to do is that since the transformation already happens, we are going to use that time that the data is being transformed to also identify what is the target bit precision for that particular data, and store that bit precision inside some SRAM inside the memory controller itself. So basically what we're trying to figure out is that when I'm transposing that data prior to process memory execution, I have an array, for example, and I'm trying to identify what is the boundary of the dynamic range of the values stored in this data array, so the upper ceiling. So what's the maximum value that I have in array B, and what is the maximum value that I have in array A that are going to be next used in an addition operation? Why is that? Because once I know the maximum values, I know what is going to be the cap bit precision for that particular process using the operation. And I can adjust the bit precision to not be 32 bits anymore, to be this cap bit precision. So for example, if I have I have array A with many operands and array B with many operands, and identify that the maximum element in array A is 7 and the maximum element in array B is 9. I know for a fact if I do addition, the maximum precision that the addition can take is log of 2 of 7 plus 9. and I can cap the bit precision to that particular value when I issuing that sequence of in-DRAM activations. And this is going to allow me to save latency doing the computation. So this is exactly what we do. Was this that clear or was too complicated? Okay, hopefully it's clear. So once I know that precision, I can probe that parallelism-aware microprogram library to identify what is the most efficient implementation of that particular in-DRAM operation, and then issue those operations, those activations according to the DRAM chip itself. So by doing that, we implement some several applications over there, and we see that we can significantly improve performance compared to prior process using DRAM system, and also improve energy efficiency as well. And this is how you can basically leverage the properties of your data to accelerate computation of those in-DRAM systems using some runtime frameworks. So is there any question about Proteus? Probably it's going to be also a reading of the semester. So the last question that we have in your adoption list here is infrastructure. So how I come about evaluate those systems, right? So if you are a Samsung or SK Hynix or a Micron, this is easier. You just build the system that costs billions, and then you test, and then you verify. And then if it's correct, you put it in the market, and then you may or may not make a lot of money. But unfortunately, we are not them. So we have to use alternative solutions to evaluate those type of systems. One way is to use FPGA-based prototyping. We do this in our lab, where we have this FPGA boards with modified memory controllers that allow us to, this is this one old iteration of the system, which allow us to issue comments to the DRAM chip as we want, independent on the independent of the time parameters that are specified. So we can violate this DRAM time parameters. And we keep building on top of this infrastructure to make it easier and easier to write codes for. So you don't necessarily need to write very low code to program this anymore. It's quite high level at this point in time. And this is open source. So initially it was called SoftMC, now it's DRAM band. Another way of coming about infrastructure is to create architecture simulators that can simulate processing memory systems. So that move is one example that has an architecture simulator built over there that's written in C++ and can simulate different types of processing memory architectures. But usually these type of solutions are quite it's quite research dependent. So you have idea for a pin architecture. So you take one accelerator, you need yourself to go modify this architecture. So write C code or C++ code or Python code, whatever, and verify that that code is correct and simulating what you're expecting. And then you run your application over there. So this is just one example of simulator. There are many examples for different use cases over there available in open source. Samsung itself has a simulator for their pin system, which is available online and you can use it. And also there are simulators from all the research group for the up-mem pin system. So if you don't need to buy this server itself, you can simulate that. And most of the simulators that we do in Safari for our projects, we try to make them available online for people to modify and advance the state-of-the-art based on them. So is there a question related to simulators? So if you do conduct research on processing memory or in computer architecture as a whole, 80% of your time is writing code and building those simulators. The idea usually, once it arrives, you spend most of your time trying to prove that the idea works, writing these simulator codes, which can be fun. Sometimes it can be very stressful as well because it's code engineering. So sometimes you have a bug and then you don't understand what's going on. But yeah, so this is very, very important to be familiar with those tools and know how to modify and change them for your needs. And again, it's not only for PIM, this is for computer architecture as a field. So if you end up, I don't know, at NVIDIA doing the next generation of their GPUs, you're also going to spend a lot of time writing C code to try to demonstrate that your idea works well. So yeah, if you like coding, this is good for you. If you don't like coding, you hire an intern or someone else, and then they code for you. And so that to wrap up, hopefully this talk was interesting for you to show that those process memory architectures are quite promising for moving forward for data-intensive applications. They are already in the market. People are talking about them. There are companies being built around them. Big vendors are developing more and more around those process memory architectures. So I really believe that this is a great time to do research on this subject. When I initially started my PhD in this field, the future of process memory architecture was quite uncertain. There was no killer application, and there were not real hardware prototypes, and so then the landscape completely changed in those 6 years of PhDs, and it's more and more of a hot topic than ever. So I'm biased, but is actually a very, very profitable topic to work on right now. And basically what this allows us is to design more energy efficient and high performance systems by moving data minimally inside the SoC itself. But adopting this can be troublesome because we need to change many things in the system, but we can look at those changes, as I mentioned in this lecture here, one problem at a time. We don't need to look at every single problem at once. You're going to go crazy and nothing's going to be done. So it's better to find a topic, work on the topic, solve that issue, and move on to the next one until you have an entire system built around that can be suitable for those data-intensive applications. I guess this concludes my talk. Is there any question related to whatever? I went too fast after the break, but it's okay. Is there any question to anything that I just mentioned today?
Does DAMO have processing using memory also, or is it processing near?
It's mostly near memory. Yeah.
So for processing using memory, use DRAM vendor or software.
Or emulator. We also open source our the SIM-DRAM simulator is available online. So it's mostly emulator based or Gen 5 based. And of course, to do the experiments in the real DRAM chips, you use DRAM vendor. Any other question? Okay, so if you are interested in reading anything more about process memory, we have this book chapter that we wrote that summarizes what I mentioned here and way more. So it's definitely a good guide if you are interested on this subject. So thank you so much for listening. Thanks for your attention and for the great questions. And I hope you get to read some of those works that I just mentioned here earlier during the semester, and you enjoy them. And if you get to read on any of my papers and you find a typo, don't let me know. Otherwise I'm going to get very stressed. Just kidding. But yeah, this concludes. Thank you very much and have a good evening.